Hi everyone. Today we're doing a Mechanics 1 paper from AS Maths. And here we have our first question. So we're talking about a block which is being pulled along a horizontal surface, and it's rough, so there's friction. Ooh, so let's look at our situation. So our block. So what forces do we have acting here? Well, it's always good to draw everything out. So we have mg, as usual, flat floor. And there's some reaction force. In fact, I'll draw that in afterwards because you'll see that the reaction force is not, in this case, equal to mg. We have this of 25 newtons. So this is going to have, we can resolve this force along the floor into a horizontal and a perpendicular component. And there's going to be some reaction force here. And there is going to be a force of friction opposing the motion. So they're asking us for the normal component of the contact force acting on B. So the normal component, normal, always means perpendicular. So they're asking basically for the perpendicular force, which is R, acting on B. So R is always that is the force the floor is exerting on the block, and that's always such to balance the force that the block is exerting on the floor. Now, if there was no force pulling upwards, the force that the block is exerting on the floor is just the weight of the block. It makes sense. Like the reaction force is just there to basically because we know that the block isn't sinking through the floor, so there must be some force balancing the forces that are asking it to sink through the floor. But we already have a bit of a force pulling upwards, so that's already kind of balancing a bit of this mg. So the reaction force is just mopping up the remainder. So we have that mg is equal to the reaction force plus 25, and then this is theta, so 25 sine theta. Well, mg we have, it's just 27 newtons, 2.7 times g. And the reaction force is what we're, R. And we're told that this is 20 newtons because we're told the normal component of the contact force. So the contact force, essentially, it's what the ground is exerting on the block. So it's R, and it's also this friction force. Equal to 20 plus 25 sine theta. And this gives you that sine theta is equal to 7 over 25. And that's it, you're done. So the second part is asking you to find the work done by the pulling force in moving the block distance of 5 meters. Well, work done is sort of force exerted over a certain distance in the direction of that distance. So if the thing is moving in this direction, we're only looking at the force which is in that direction. So we don't care about the up and down force for this problem. So work done is, it's an energy, right? So it's the energy you're basically putting into the system to move it along 5 meters. Now, it's pulled at constant speed, right? So that means that there's no acceleration you have to worry about. So all of that work is going into fighting the friction force. So this is just equal to the friction force times the distance. Well, the friction force is just mu r, and the distance we're given. Well, what is r? R is just 20 newtons. So this is so distance is 5. Sorry. Okay, here's a subtlety. That's my mistake. So don't make this mistake. Mu r here is like net r. So it's the r which it's kind of you know what? I'm being silly about the whole thing because we're not given mu. We're not given R. We're told already that the pulling force has a magnitude of 25 newtons. Therefore, this horizontal pulling force, the one that's balancing the friction force. So you see that it's not accelerating. So these two things have to be equal. And this is just 25 cosine of theta. Therefore, this must be 25 cosine theta. So we have that the work done is the force, which is 25 cosine theta, times the distance, which is 5 meters. We already have the sine of theta, so you know that the cosine of theta is equal to the square root of 1 minus sine of theta, sine squared of theta. Or you might just plug into your calculator theta, the cosine of theta is the cosine of the inverse sine of 7 over 25. All these are fine. They will give you the right answer. And so that gives you the work done. Okay. So question 2. Again, this one is just balancing forces. So what do we have? We're told that this thing is in equilibrium, which means it's not moving. So equilibrium, net force is equal to 0. And that applies in both directions. X and Y, you can individually know that they're 0. So what is the net X force? Well, that's along this horizontal direction, right? So you have a bit of this force, which is going to be F cosine theta. And you have a bit of this force, which is going to be 25 cosine of that angle there. And this force down here doesn't contribute in the x direction at all. So that x force, let's say in the positive x direction, is F cosine theta minus 25 cosine of the inverse tangent of 0.75. Because that is just the angle of that force. It's called alpha. So this is one equation, and we know this thing is equal to 0. So if we solve this, we get that the F cosine theta must be equal to 20. Well, we still have two unknowns, so we need another equation to be able to find out what these are individually. Well, we can use the y component. Of what I called alpha, this thing, minus 63, because this thing is acting completely in the negative y direction. And this is all equal to 0. So this will give you that f sine of theta is 48. And now we have what we need. So if we take this equation 2, and we divide it by equation 1, we get that the tan of theta is equal to 48 over 20, which is 12 over 5. And that's one of the things we're asked for. And then we're asked to find f, and you can just find that by plugging this thing back into this. You can say that f is equal to, say, 20 over the cosine of theta, which is the cosine of the inverse tangent of 12 over 5. That's all done. Okay, question 3. So we're given another ramp. So we're told that we have a block on this ramp. And this is some angle theta, which is this inverse tan of 11 over 60. They really like this inverse tan in this question paper. Okay, so we have some block and it's sliding down a slope. And it passes some point A here. And then at some point it comes to rest because you've got friction fighting it, right? So this is it's one of those occasions where you really should, even though you're talking about something in motion, you should really just use conservation of energy, because conservation of energy is always much easier than dealing with kinematics. By kinematics, I mean things like time and velocity and stuff like that. Well, velocity will enter this question, but you want to avoid dealing with time if you have to, because that's when things get a little complicated. What we have is conservation of energy. So let's talk about the change in energy from A, let's call this B. So let's delta kinetic energy, delta meaning change in. Well, that's just going to be equal to 1/2 mv at a squared minus what the kinetic energy at b, but it's at rest at b, so there is no change. So what about the potential energy? So this is going from A to B and A to B. So just be careful that you're evaluating it like from A to B. So actually, I wasn't careful. It actually has lost potential energy, so this should be a minus, because it's actually 1/2 mvb squared, which is 0, minus 1/2 mva squared. So you always go like, energy at the final point minus energy at the initial point. You can do it the other way around too, but you just have to be consistent. So there's definitely, as it's gone from A to B, it has lost kinetic energy. Now, what about potential energy? Well, what's the potential energy at B? Let's call the potential energy at B 0, and then we're going to subtract mgh. So it's lost potential energy as well. Well, what is h? H is this distance. So h is this distance times 0. So that's going to be minus mg, and then say this is d, mg d sine of theta. So this is the total energy, the change in energy, as you're going from A to B, is equal to minus 1/2 mv squared minus mg d sine theta. Well, where is the energy gone? Well, it's been dissipated in friction, right? I mean, that's the only way you can lose energy between 2 points is when it's dissipated through some sort of friction force. So we're told that there is a coefficient of friction between the block and the slope. So this is going to be equal to the work done by friction. Well, this is going to be the force of friction times the distance traveled, which is this hypotenuse, which is mu r d. Well, if I'm thinking of my block, if I'm thinking of my block sitting here, the weight is acting. The reaction force is like so. It's moving in this direction, so the friction force is acting like that. And then I'm resolving this along these two directions. So this component of the weight is mg sine theta. So it should be mg, right? So the reaction force is going to be mg cosine theta. So this is equal to mu mg cosine theta times the distance. So we're solving for the distance, right? We have everything else. We have the mass. We have the velocity at the beginning. We have the mass. We have, in fact, the mass all divides out. We have g. We have theta, so we can get sine of theta. We have cosine theta. We have mu. So we can solve for d. No problem. Conservation of energy. So we got the difference in energy between these 2 points, and then okay, so there's a little bit of subtlety here. I said that the change in energy was negative. Now this work done in that case must, this is actually work done by the block on the ramp, the friction exerted in like heat of molecules as it vibrates them and stuff. In fact, if I want this equation to work, this has to be negative, because I should be talking about the work done on the block. Now, of course, no work is being done on the block is doing work on the ramp, but that just means sort of you just make the work negative. So actually this should be negative, 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 negative. So the negatives all cancel out. So sorry, I should I should actually just have talked about the change of potential energy sort of the other way around, like a sort of the loss. So I could, just to make it absolutely clear, I could talk about loss of energy, which is the positive 1/2 mv squared plus mg d sine theta, is equal to the work done on, or let's say by, block, which is equal to mu g cosine theta mu mg. So I hope that that's a bit clearer. Okay, question 4. So now we have, well, the first question we have here is quite obviously a conservation of energy question, because they've deliberately asked us for the energies. So we have a lorry moving from O to A and then down to B. So it's going along, we're told it's a straight horizontal line, and then it goes downhill some. And this angle we'll call theta. And we're told that this is 400 meters and this is 300 meters. And we're told that it's at rest here, and that it has some velocity there. So for the motion from O to B, so from the beginning to the end, find the gain in kinetic energy. Well, so we're going to say delta KE is equal to, well, it's at rest at the beginning, so it's just the final 1/2 mv squared, which I'm going to actually just give the numerical value, and I'm going to do this in scientific notation, which is worth learning, because when you're dealing with these like massive amounts of energy, it would be ridiculous to write this down. And let's talk about the loss of potential energy. So it's a loss, it's going to be negative. So it's going to be the potential energy at B, which we're going to just say set to 0, and then minus the potential energy at A. So this height that it's changed is going to be 300 sine of theta. So this is going to be minus mgh, which is minus 4.2 times 10 to the 7 sine of theta joules. So that's just question 1. So now we're going to use these facts, and we're going to say we're going to evaluate it against like the resistance to motion. So we're told that there's this much resistance to motion, this much force acting against the lorry, and that the complete the work done by the engine is 5,000 kilojoules. So all of that work has gone into fighting the force of friction, and so we can balance this. So we can say that the work done by the engine is equal to the gain in energy. And if the gain of energy is negative, it means you've got energy loss, plus the force, the resisting force times distance. So that's the resistance to motion. Well, the work done in the engine, we're told, is 5,000 kilojoules. So that's 5 times 10 to the 6 joules, right? And I'm going to stop writing joules because everything's going to be in joules. And this is equal to the gain in energy. Well, it's gained some potential energy. So it's 4.032 times 10 to the 6. But it's lost potential energy. So it's minus 4.2 times 10 to the 7. So you can see it's actually lost energy in net energy, but so it's just a negative gain in energy. Sine theta, probably. So then you have plus the resistance to motion times distance, which is going to be that 4.8 times 10 to the 3 newtons times 400 plus 300 meters gives you 3.36 times 10 to the 6 joules. So you can see the only non-number here is sine of theta. So you can easily solve to see that theta is really small. It's like 3.3 degrees. So conservation of energy. The big difficulty with these things is getting the signs right between these, like the work done by the engine. But always think, okay, I'm going to focus on the lorry itself. So I'm going to talk about work done on the lorry by the engine. Then that has to be equal to whatever energy that then the lorry then did on the ground, which is the resistance force, fighting the resistance force, plus, and if there was anything left over, that would go into the internal energy the energy of the lorry, which might be kinetic energy, it might be potential energy, a combination of those two. So this makes sense. Like, this is all that the engine has got to give, and that goes into fighting the resistance force. And if there's anything left over, giving the truck some energy. Okay. So, question 5. So this is one of those power questions. So I think the best thing always is to remember is to try and get things into some combination that we can use. So we're not given really anything about time. So we know that power is energy over time, but we're not told anything about time. So I'm going to multiply this by distance over distance, using S for distance. Well, this is just energy over distance times distance over time. Well, that's distance over time is just velocity. So in fact, I'm going to actually do this in differential form because this is kind of an oversimplification. Strictly speaking, you should say that P is equal to dE dt, which using the chain rule is equal to dE ds dt. Well, this is just velocity, which is equal to velocity dE ds. And then we can look at the work. So the work done. So work done we know is just which is an energy. And we usually think of it as force times distance, but really it should be the integral of the force over the distance, because the force might depend on distance. If the force is just a constant, this just becomes force times distance if F is a constant. So that's recovering that expression. So you can see that this implies that the force, so this integral expression implies that the force is just dE ds. So if we plug that back in there, we get that P over V is equal to F. So this is the driving force. Okay, good. So so we know that we have two situations, one where the cyclist is moving uphill and one where she's moving downhill. And these need to be evaluated separately. So let's first look at the uphill. So in this scenario, you have the cyclist here, and you have the driving force moving her uphill. So you know that because she's moving uphill, the force of friction is acting downwards. And you also know that the component of her weight is also acting downwards. So it's like the force of friction and her weight are both like teaming up in this case to fight the driving force. So the driving force, so the net force pointing uphill is going to be the driving force minus the force of friction, the resisting force, minus mg sine theta. And this is equal to mass times acceleration. So if we plug that in, the driving force is P over V. So we're told in this case what V is. So it's P over 3 minus the friction force, which we're told is R, minus 84 times G times 0.1. And that's equal to 84 times 1.25. And this is an equation in P and R, so everything else is numbers, so we can't solve yet. But let's talk now about the downhill case. So you just have to be a bit careful. You have to evaluate these separately, because now you've got the driving force going down here. She's moving downhill, therefore the friction force is acting opposite to that, which is uphill. But now the component of her weight is sort of is helping the driving force against the friction force. So the net force acting, well, let's talk about it. Yeah, acting downhill is the driving force acting downhill plus her weight, which is mg sine theta, minus the friction force. So you see the weight has changed sign between these, and this is equal to ma. In fact, I have been a bit silly and needlessly confusing. I'm going to actually be a bit more rigorous here, and I'm going to define our positive direction as up, right? Because here the acceleration is, if acceleration is positive, which it is, she's moving uphill. Here we want that acceleration to be of the same sign if she's moving up. So of course we want it to be negative in this case, because she actually is moving up. So this is actually equal to the force of friction minus the driving force minus mg sine theta, and that's equal to ma. So I'm just being super careful. So in which case the a that you would plug in here would be negative, whereas here it would be positive. But that's just kind of to make sure everything is legit. In here it won't actually make a difference if you go the other way. But remember that negative, things are just about directionality. So just do what I do and just make sure you just clarify what you mean by positive. So this symbol, this is just my personal notation, but this symbol sort of means that a positive directionality means uphill. And you might, when you have some axis, you might be defining like the positive to be in the x direction or positive y direction or whatever. But as long as you're consistent, you will never run into a problem. Okay, question 6. Just the last piece is that this thing, this will get you that the force of friction, which is R minus P over 10 minus blah 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 is equal to blah, and then you get two equations in R and P, and therefore you can solve for R and P. So you just add them together in creative ways, and you solve for one, and then you plug in and get the other. So that should be fine. Okay, question 6. So this is all about kinematics. So you're going to have to use the acceleration equations. And in fact, you're going to have to be careful because you can't use the constant acceleration equations, because as you can see, the acceleration is not constant. It depends on time. So I sort of went through this on Tuesday, but you can, if you just quickly think about it, you know that the acceleration is equal to dv dt. So if I separate variables, I get that dv is equal to a, and we're saying acceleration depends on time, right? So it's a function of time, dt. And then I integrate both of these, let's say from 0 to v, and from 0 to some time t. Well, that means that the velocity is equal to the integral. So I can't do any of I can't actually do the integral until I know what form the acceleration is. So the velocity isn't just acceleration times time. That only works if the acceleration is a constant, in which case it comes out of the integral and this thing just integrates to t. But we have to be careful now. So in this case, this is v as a function of time. So we want a's velocity when t is equal to 200 and when t is equal to 500. So v at 200, well, that's just equal to, and I'm going to integrate this velocity that they've given, this acceleration that they've given us. So it becomes 0.05 t minus 0.0001 t squared. And that's evaluated between 0 and 200. And if you do that, you find that it gives you 6. And then we're going to look at what it is at 500. Well, that's just going to be exactly the same thing, but evaluated between 0 and 500. And you'll find out that that's actually 0. Okay. So that's done. So the only sort of subtlety that you need to know is that you need to integrate. Okay, so now we're looking at B, and we're told that when at 200 seconds and at 500 seconds, that it has the same speed as A. So we know that V at 200 seconds is equal to 6, and we know that the velocity at 500 seconds is equal to 0. And the acceleration of B is constant. Between 0 and 200, it's one value, and between 200 and 500, it's another value. So it's accelerating until 200 seconds when it starts decelerating. So we know this 6 must be equal to the initial acceleration, times 200 seconds, because it's constant, right? So we can just use the constant acceleration equations where V is equal to acceleration times time. Well, it's actually equal to the initial initial velocity plus acceleration times time, but at t equals 0, B is at rest. So it's just acceleration times time. So this means that A1 is 0.03, so just divided. And we know that this final velocity must be equal to V at 200 minus, plus A2 times the time between those 2 points, which is 300. And this gives that A2 is equal to minus 0.02. So it's a deceleration, it's a negative. Okay, so we know these two facts, and we know everything about that B's motion. So let's work out the distance traveled by B. Well, let's say just in the first bit, it starts with an initial so it starts with initial velocity of 0. So all of the distance traveled is 1/2 A1 times t squared. And we know that at the second part, we start out with the velocity at 200, which is 6, times the time that's passed in this next section, which is 300 seconds, plus 1/2 acceleration to 300 squared. And remember that this is going to be negative, so this is going to come in and make this negative. And we find that if we add these two together, we get 1,500 meters. Particle A. So this was all particle B. So now it's just slightly more complicated in the fact that we have to use this integral expression again. So we know that ds dt is velocity, and therefore in the exact same reasoning as we had before, we have that s of t is equal to the integral of v of t dt. Well, what is v of t? We already got it because it came from our integration of the acceleration. So this is going to be integral of 0.05 t minus 0.0001 t squared dt. So this, in fact, so let's talk about the one at 500 seconds. It's going to be the integral from 0 to 500, and I'm going to integrate this. So it's going to be, 0.05 over 2 t squared minus 0.0001 over 3 t cubed, all evaluated between 0 and 500. And you'll find that this is 20883. And then, so delta S, the difference between them, you can easily get. So what did we do in this question? Well, we emphasize that these things are obtained by integration when you have non-constant acceleration. And you just have to be a little careful with signs, make sure that you're doing everything consistently and giving things the right sign. Otherwise, I think that's not too bad of a problem. If it helps, absolutely draw a, just even if it seems really trivial, draw a sort of map in your mind. So this is at 0, this is at t is equal to 300, 200, and then t is equal to 500. For some reason, this just helps me just to sort of get it clear in my mind. Hopefully I'll help you. Okay, so last question. So this one's a bit of a, they spend quite a lot of time. Oh, okay. Spend a lot of time describing it, but essentially you have two time periods. You have the time period after after the whole system is released from rest, but before the string breaks, and you have the situation after the string breaks. So let's look at before the spring breaks. So we're finding the speed of B immediately before it hits the floor. That's our first task, and they've given us like 9 marks for this. So before breaking. So it's going to be a multiple step question, which is why there's so many marks. So let's look at B. Well, what are the forces acting on B? You have the tension in the string, and you have mg. So therefore, the net force, and I'm going to define the positive as acting downwards. So the net force downwards is mg minus t, and that must be equal. And this is, sorry, I should make it clear this. I'm talking here about the mass. I don't know why this thing does this. mb times g, the mass of B, which is equal to mb times the acceleration. Now I'm going to look at A. Now for A, the only force acting on it is the tension. Sorry, the only external force, and then it's got some force of friction. So this is the force, and I'm going to define the positive direction as heading that way, because, I mean, that reflects the way the whole system is moving. It'd be the same, you know, it means that both accelerations will be the same. So acting this way, the net force is T. Oh, so this was mg minus T. And here it's T minus the force of friction, which is T minus mu ma g. And that is equal to ma times acceleration. So the key things to remember is that the acceleration here is the same in both, and so is the tension, because the string, you know, because it's a light, inextensible spring. It can't It can't have different tensions, different stretch, or become loose, or different stuff. So essentially, think of it as like a flexible rod. So it's really stiff. So the tension is always going to be the same everywhere, and we know that the system must be therefore accelerating all at the same speed. So if we take these two and we add them together, we will get that the acceleration is mu mag minus mbg all over ma plus mb. So just, you know, be careful when you're putting the masses into your individual equations. You have to make sure you keep track of which mass is which, because they're different, and that's going to affect the force on them. So that is expression for acceleration, and then we can also just use that. So that will give us 6.4, and that will also give us the tension if we want it. But in fact, in this case, we don't even need the tension. We just need the acceleration, because we're talking about the motion of this thing. Okay, so we've got before the thing breaks, and it breaks at 2.5 seconds. So before it breaks, so at breaking, we know the thing is accelerating at some constant rate, 6.4 meters per second squared. So the B starts at rest. So what is its velocity? Velocity of B when the string breaks at 0.25 seconds. Well, that's just equal to the acceleration times 0.25. So the velocity of B when the string breaks, not when it hits the ground, but when it breaks, is 1.6 meters per second. Well, after breaking, what are the forces on B? Well, it's just free falling, right? So all you have is mBg. So therefore, the net force, which is equal to mBg, is equal to mBa. So, the acceleration is just g. That's the thing. When you're in free fall, in gravitational potential, all you're feeling is g, and that's your acceleration. So therefore, the velocity, we can find the velocity from conservation of energy. So actually, I should have put this here, is that at the time of braking, the distance traveled is just half mb times time squared. And you'll find that this means that it's traveled 0.2 meters. So it started off 0.5 meters up. And then when you had this braking, it's now 0.3 meters up. So now we can, for the last bit of the question, we can use conservation of energy. So at the point that it broke, it had 1/2 mv squared kinetic energy, and it also had mgh, where h is 0.3, potential energy. Now this must be equal to its total energy when it hits the ground, which is all kinetic because it's at the ground, so there's no more potential energy. 1/2 mv prime squared. Well, m's cancel, happily. We have vb, the velocity when the string broke, which we found there. We know g, we know h, and therefore we can find v prime. And that is the solution to the equation. We get that v prime is 2.6 meters per second. So that was most of the question. The very last piece, we have to find the total distance traveled by A. Well, this again is just a conservation of energy equation. In this case, there's no change in potential energy of A. There's a change in kinetic energy, so we're told in the question that A does not reach the pulley in the subsequent motion. That means that it slows down, it loses all its kinetic energy, and it stops at some point. Well, where is this kinetic energy going? Must be to friction. So we know that the horizontal distance traveled by A at braking the distance at 0.25 seconds is it got to be the same as B, right? It has to travel the same amount because they were connected by a string that didn't stretch. So 0.2 meters. And that its velocity at that same time was, again, exactly the same as B because they're traveling kind of as a unit. So we know that the kinetic energy that it has at this point, so kinetic energy is 1/2 mv squared. And if it's now at rest, sitting on the table at rest, at the end of its motion, then so at the end, it's at rest. So all of its energy is 0. There's no kinetic energy, no. Well, it's got potential energy, but the change in it's lost all its kinetic energy anyway. And where has that gone? It's gone into work done against the friction force. So work done against the friction force, so friction times distance traveled, is equal to the kinetic energy. Well, we know what the force of friction is. So we can solve that the distance is equal to 1/2 mv squared over the force of friction. The force of friction is just mu r, which is mu mg. And that will give you the correct answer. So actually, I didn't need this bit. But what I needed was the velocity at the point of braking. So the whole thing moved as a unit until the string broke, and then they start their individual motions. So in both cases, we could use conservation of energy to find out some facts about them. And that's the end of the paper. Please let me know if you have any questions.